Hello and welcome to Mech Zone. Till the last lecture, we have finished studying about the basics and all theories about heat exchangers. And in the heat exchangers, we studied that it is of actually three types, that is direct contact type, indirect contact type, and the third was another classification. Now today, we will be starting an all new topic, that is radiation, and we will be studying all the theories about it and specifically radiation in detail. So I have already explained to you in the basics of the heat transfer when I was discussing in the lectures 1, 2 and 3. You can watch all these lectures on my YouTube channel Mech Zone, and in that lecture we have discussed only the basic parts of conduction, convection and radiation. I also then explained about in detail conduction, and now is the turn for radiation. So for example, say we have a vacuum chamber. For example, this is a chamber such that we have maintained vacuum in this chamber. We have two plates inside this chamber. We have two plates inside this chamber such that this is the HT and this is the LT. HT is the high temperature plate, LT is the low temperature plate. And the temperature of this plate is very high such that the inside cavity is vacuum. Now if this system is left undisturbed for some point of time, then we will observe that both the high temperature plate and the low temperature plate have been in thermal equilibrium. अगर हम इस पूरे सिस्टम को थोड़े टाइम के लिए छोड़ देंगे तो हमें ये दिखेगा कि जो हाई टेम्परेचर प्लेट है वो लो टेम्परेचर प्लेट के साथ थर्मल इक्विलिब्रियम में आ चुकी है. Now since we have both the bodies in thermal equilibrium, we can say that some energy would have definitely left the high temperature plate and would have reached the low temperature plate. तो कुछ ना कुछ एनर्जी ज़रूर होगी जो हाई टेम्परेचर प्लेट को लीव करके लो टेम्परेचर प्लेट पर गई है, सच दैट ये जो एनर्जी है हमारी इट हैज़ ट्रैवल्ड थ्रू वैक्यूम, क्योंकि ये हमारा वैक्यूम था. दिस इज द इवैक्यूएटेड चेम्बर. ठीक है. So it confirms that some amount of energy must have been exchanged between the high temperature plate and the low temperature plate, even in the absence of any matter, that is in the presence of vacuum. And this energy, the energy was exchanged in the form of electromagnetic radiation. Electromagnetic radiations. Okay, so the energy which was released from the high temperature plate and it reached the low temperature plate must have been in the form of electromagnetic radiations, because electromagnetic radiations possess a property that they can travel through vacuum. Okay, so emissions will electromagnetic emissions were given out from the high temperature plate and they reached the low temperature plate. So we will say that all bodies at all temperature, all bodies at all temperatures emit radiations except at 0 Kelvin. At all the temperature values, all the bodies will emit certain type of radiations except 0 Kelvin. अगर बॉडी का टेम्परेचर 0 केल्विन है तब हम इसकी बात नहीं कर रहे हैं किसी भी रेडिएशन को एमिट करने की. हम सिर्फ और सिर्फ तभी बात कर रहे हैं जब बॉडी का टेम्परेचर 0 केल्विन के अलावा कुछ भी है, बिकॉज 0 केल्विन पे क्या होता है, हमारा मॉलिक्यूलर मोशन पूरा सीज हो जाता है. ठीक है, तो हम लोग 0 केल्विन की बात नहीं करेंगे. ठीक है. और एक चीज है जो हमें याद रखनी है, दैट इज इफ द रेडिएशन जो कि एमिट हो रहा है एंड इट इज करस्पॉन्डिंग टू हाई टेम्परेचर, it is corresponding to high temperature radiation, then the wavelength would be, that is lambda would be less. It will be a shorter wavelength radiation. The radiation which is corresponding to the high temperature would be shorter wavelength radiation. Wavelength will be shorter, and the radiation which is from the low temperature low temperature radiation will correspond to lambda, which is more or longer wavelength So this inverse relation we have to remember. Or we can write, if the temperature is more, then energy will definitely be more, such that lambda will be less. So we can summarize it in just one single box कि अगर टेम्परेचर ज़्यादा है तो इसके करस्पॉन्डिंग हमारी एनर्जी भी ज़्यादा होगी, एनर्जी कंटेंट ज़्यादा होगा, और हमारा जो वेवलेंथ एमिट होगा दैट विल बी ऑफ शॉर्टर वेवलेंथ. रेडिएशन टॉपिक को एक्चुअली हम लोग दो सब पार्ट्स में भी स्टडी कर सकते हैं, एक्चुअली दो मॉड्यूल्स में स्टडी कर सकते हैं. तो द फर्स्ट मॉड्यूल इज द वेवलेंथ मॉड्यूल एंड द सेकंड इज द डायरेक्शनल मॉड्यूल. In the directional module, we assume that the radiation is being given out in almost every direction. So the radiation is being given out in every direction. So we call it as hemispherical direction. For example, from this point also the radiation is being given out in every possible direction. If we consider this point, then also radiation is being given out in every possible direction. So this is called as the directional module. Whereas if we talk about the wavelength module, then the lambda or the wavelength at which a particular energy, or it is also, we will see it in the lecture later, it will be called as monochromatic or spectral emissive power. Okay, so micrometer. This wavelength is given in micrometer. ठीक है, तो this will become the wavelength module in which there is some relation between the wavelength, and in the directional module we will say that the radiations are given out in almost all possible directions, that is in a hemispherical form. Okay, now we will start with some basic definitions in radiation. The first is capital E. This capital E is called as the total hemispherical emissive power. Total hemispherical emissive power. I am not going to write the entire definition in the paper, but I'll be dictating it so that you may also write it down. So actually it is defined as the radiation energy which is emitted from the surface or a body. It is defined as the radiation energy emitted from a surface or a body per unit time and unit area in all possible hemispherical directions. Okay, this is called as the total hemispherical emissive power, represented by E. The unit of E would be joule upon, we have per unit area means meter square and per unit time means second. So it becomes, and we know that joule per second is watt. So the unit becomes watt per meter square. So the unit of total emissive power becomes watts per meter square. Okay, we now come to the term emissivity. Say for example we have two surfaces. Okay, one is temperature, one it is at a temperature T1 and the other is also at a temperature T1, such that the temperature of both the surfaces are same. One is a non-black body and the other is a black body. Okay, these are identical shapes, they are both having the same temperature. So the radiations which will be given out by the non-black body will be lesser in magnitude, less radiations, whereas the radiations which will be given out by the black body will be much more as compared to the non-black body. So we have more radiations. Okay, now emissivity is represented by the symbol epsilon. it is equal to, actually it is defined as the ratio between the total hemispherical emissive power of a non-black body, let it be E. E is the total hemispherical emissive power of a non-black body divided by the total hemispherical power of the black body. EB is the total hemispherical emissive power of the black body, and E is the total hemispherical emissive power of a non-black body, such that capital E is equals to epsilon into EB. Capital E is equals to epsilon into EB. Where symbols we have already discussed that epsilon is the emissivity. Okay, now we know that emissivity of a black body, epsilon of a black body, okay, epsilon of a black body, or not for a black body, if we discuss it for any general surface, epsilon for any surface, epsilon for any surface can always be less than or equals to 1. It is always less than or equals to 1. Equal to 1 for black body, equal to 1 for black body, and less than 1 for any general body, for any general body. So the value of epsilon, this question can also be directly asked, that emissivity of any surface can have what value. So it can have any value less than or equal to 1. Okay, less than or equal to 1. Now what is actually a black body? What is actually a black body? Now I have also discussed this topic in my earlier lectures, so I'll discuss it again. That a black body is one which absorbs all the radiations, which absorbs all the radiations, which absorbs all the radiations which is incident on it or falling on it. For example, if this is a body such that this is a black body, okay, and if the radiations are falling on this body, so it is absorbing all those radiations which are falling upon them, such that there are no reflections or transmission, no reflection of this radiation and transmission. There is no transmission. This radiation is not crossing this body and it is going outside, so there is no transmission. Okay, so we can call it as a perfect absorber, and ideal emitter, perfect absorber and ideal emitter. This is the main point which needs to be remembered in case of the black body, and it is diffusive in nature. It is diffusive in nature. Okay, it is diffusive in nature. Now we will discuss about an example of a black body such that this is a cavity. Say this is a cavity and there is a very, very small hole in this cavity such that the external of this cavity is being insulated. Okay, now if we allow a ray of light to enter this cavity, which is very, very small, so this ray of light will definitely come inside and hit this surface. Now after striking this surface, it will be reflected, and it will be reflected here. Now again it will undergo reflection here, again reflection here, again reflection here. So we can say that this ray of radiation, this radiation ray will be completely internally reflected within this cavity and it will be absorbed by this body in the inside chamber. Okay, now actually what is happening is this cavity in this body can be treated as a black body. This cavity in this body can be treated as a black body. The incident which is the radiation which is incident on this body is being completely absorbed after multiple internal reflections. Okay, it is being completely absorbed after multiple internal reflections. For example, a small cavity or a tiny hole in a furnace wall. If we talk about a furnace wall, then a small hole or a tiny slit in this wall can also be considered as a black body. This hole is being made in the furnace wall, in the furnace wall. Okay, so this can also be considered as a black body. Now in our daily analysis or in the analysis of radiation, sun is also treated as a black body. हम लोग sun को भी क्या मान के चलते हैं, black body मान के चलते हैं. ओके और मैंने ये भी पहले बताया था कि a black body doesn't need not to be appear to you black. जरूरी नहीं है कोई भी ब्लैक बॉडी आपको ब्लैक दिखे, ठीक है. फॉर एग्जाम्पल स्नो जो है, स्नो इज ऑल्सो कंसिडर्ड एज अ ब्लैक बॉडी बिकॉज इट हैज हाई एब्जॉर्प्शन नेचर फॉर इंफ्रारेड रेडिएशन. इट हैज हाई एब्जॉर्प्शन नेचर फॉर इंफ्रारेड radiation. Since it is absorbing all the infrared radiation, so snow will also be called as a black body. Okay, now next topic that we will be discussing is monochromatic or spectral emissive power. Monochromatic or spectral emissive power. Now it is same as that of the total hemispherical or emissive power that we have studied earlier, but now we have the symbol as E lambda. So definitely this energy would be radiated at some wavelength. Okay, so it will be defined as E lambda is actually radiated at some particular wavelength. Okay, and it is the amount of energy corresponding to a particular wavelength. For example, if any surface E lambda is being emitted such that it is corresponding to a wavelength lambda, so it will be monochromatic or spectral emissive power, such that the total emissive power is equals to E lambda d lambda. Now what will be the unit of this monochromatic spectral emissive power? The unit would be watt पर मीटर स्क्वायर, तो होगा ही होगा. एंड क्योंकि ये पर्टिकुलर वेवलेंथ के लिए भी है तो वी विल राइट माइक्रोमीटर. वॉट्स पर मीटर स्क्वायर पर माइक्रोमीटर. ओके, एंड फॉर एनी बॉडी एट अ गिवन टेम्परेचर E lambda is actually a function of lambda. For any body at a given temperature, E lambda is a function of lambda. Okay, E lambda is a function of lambda, or it is a function of temperature. Okay, it is a function of temperature. Now say if we draw a graph between E lambda on the y-axis and lambda in micrometer on the x-axis, and the graph is like this. So the area which is being occupied under this graph, actually gives the total emissive power. This gives the total emissive power. Okay, so we can write total E here is actually the integration from 0 to infinite. We will take it from 0 to infinite, or we can also take the limits from 0.1 to 100. Okay, so if the temperature of the body is increased somehow, if the temperature of the body gets increased, then this graph is not going to be here. The graph is going to be something else in the shape. Okay, the graph is going to be something else in the shape. Okay, now we will be discussing about monochromatic emissivity. Monochromatic emissivity. It will be represented by epsilon lambda, and that will be equals to E lambda upon EB lambda. EB lambda is the monochromatic emissive power corresponding to the black body, and E lambda is the monochromatic emissive power of a non-black या any other body. So it will be the ratio between these two quantities, and it will be called as monochromatic emissivity. So from here we can write E lambda equals EB lambda into epsilon lambda. Just we have to cross multiply and we have to write it. Okay, now A body whose monochromatic emissivity is E lambda. E lambda is epsilon lambda, monochromatic emissivity epsilon lambda is independent of the wavelength lambda, or rather remaining constant with lambda. Okay, a body such that epsilon lambda is not a function of the wavelength. A body such that the monochromatic emissivity is not a function of the wavelength, then such body will be called as a gray body or gray surface. Such body will be called as a gray body or a gray surface. So a body in which its monochromatic emissivity does not depends upon its wavelength, it will be called as gray surface or gray body. Now if I draw a plot between E lambda, that is monochromatic emissive, total hemispherical emissive power correspond to a particular wavelength, such that we have three curves. The third curve is like this. Okay, so this curve will be for the black body, this curve will be for the black body, this smaller curve will be for the gray body, and this red curve will be for the non-gray body. This gray curve would be for the non-gray body. Okay, now we will come to another important topic, that is absorptivity, reflectivity and transmissivity. Okay, absorptivity is represented by the symbol alpha, reflectivity is represented by the symbol rho, and transmissivity is represented by the symbol tau. Say for example, we have a body, any general body, such that some amount of energy is being incident on it, say 100 watts. 100 watt of energy is incident on it. So after striking the surface, some amount of energy will be reflected back into the same medium. Say for example 25 watt of energy was reflected back. Some amount of energy will be absorbed by this material, say about 50 watt, and some energy will definitely cross this surface or cross this body, say the remaining would be 25 watt. Total 100 watt of energy is coming, out of which 25 is reflected back, 50 is being absorbed, I must write it, absorbed, this is reflected, and this is transmitted, and this is transmitted. Okay, now how is alpha? Alpha is absorptivity. It is defined as the amount of energy which is absorbed, that is 50 watt, upon the total amount of energy 100, so it becomes 0.5. Rho. Reflectivity is defined as the amount of energy which is reflected, that is 25 watt, upon total amount of energy 0.25. Transmissivity, tau, is defined as the amount of energy which is transmitted, that is 25, divided by the total amount of energy 100 is 0.25. Okay, so we have absorptivity, reflectivity and transmissivity as the fractions of the total amount of energy reflected, absorbed or transmitted upon the total amount of energy which is striking the surface. Now very important points: for any surface alpha plus rho plus tau should be equal to 1. Okay, if we talk about an opaque body, then for the opaque body there is no transmission, tau equals to 0, such that alpha plus rho equals to 1. Okay, if we discuss for a black body, if we talk about a black body, such that we know alpha of the black body is 1, since epsilon is 1. Epsilon means the emissivity is 1. Ideal emitter and perfect absorber. Perfect absorber means alpha equals to 1 and epsilon was 1. If we talk about a white body, A white body is one which reflects everything, so reflectivity becomes 1. And if we talk about a transparent body, if we talk about a transparent body, a transparent body is one which transmits everything, so transmissivity equals to 1. Okay, if we talk about gases like O2 and N2 such that they are diatomic gases, these are diatomic gases, so they have high transmissivity, they have high value of tau, so they are actually more transparent type of gases. These are more transparent type of gases, that is O2 and N2.